feels anything and everything is the same. No, actually you'll feel that. So they can exert a force on the free electrons and protons in the ionized hydrogen. The force exerted on each particle is the rate at which momentum is transferred to it. So as these photons come out, they transfer the momentum from themselves to the gas, and the rate of momentum transfer depends in turn on the particle's cross section for interaction with photons. Again, important thing to keep in mind: if you don't have whether or not you will meet somebody or collide with somebody depends on the cross section of that meeting or collision. Electrons have a much larger cross section for photon interactions than protons do. For instance, or for electrons, the relevant cross section is the Thomson cross section, which is given by 6.65 times 10 to the minus 29 meters squared. That's the cross section of electrons interacting with photons. So by the way, remember how in the cosmic plasma in the Big Bang we talked about the photons, electrons, and positrons being part of that cosmic jungle, interacting with each other, staying in equilibrium. This is the sort of thing that was happening even then. The electron experiences an outward force due to radiation pressure. The amplitude of the force is equal to the momentum flux times the electron's cross section. So, because what momentum are you giving to the electron depends on its cross section times that momentum to begin with. So all of that L over whatnot, that whole thing, L over 4 pi r squared over C times the sigma E, or the cross section of the electron. As the electron is accelerated, now it's accelerated because it's been hit by a bunch of photons that are coming out. It drags the nearest proton with it. Goodness, which maintains charge neutrality. Thus, so it's like hitting every hydrogen atom's electron, which then drags the proton with it. So every electron is now burdened with a massive proton that it drags along like a ball in a chain. There you go, ball and chain right there. The inward force on the electron-proton pair is provided by gravity. So it's being pushed away by the radiation pressure, but it's being also held, if you will. The inward force on the electron-proton pair is provided by gravity, which is the negative g m black hole mp over r squared y mp, because mp plus me, mass of electron, is much smaller than the mass of the proton. So this is what pulls the atom closer, but the radiation pressure is what pushes it outward. So the maximum possible luminosity for the accreting black hole is called the Eddington luminosity. So now we have two things. One is the radiation pressure given by what we just talked about, the luminosity over the 4 pi r squared over C times sigma E, which is the cross section of interaction between photons and electrons. Then we also have the F gravity, the force of gravity on this hydrogen atom, which is going to, in there, we will mainly consider the mass of the proton because it's much bigger than the mass of the electron. Then we can kind of set these two together equal to each other, because this is sort of the limit. You can't have just more and more luminosity, because as you have more and more luminosity, you also have more and more radiation pressure, and at some point that radiation pressure will push you away, push the material away. And in this case, we're considering the material to be hydrogen atoms for simplicity, and the universe does mainly only have hydrogen as its most abundant element. So the maximum possible luminosity for the accreting black hole is called the Eddington luminosity. Sometimes we just say Eddington limit after the astronomer Arthur Eddington. The Eddington luminosity is the luminosity at which this outward radiation pressure, force, whatever you want to call it, exactly equals the inward gravitational force. So set those two to be equal, like I was saying. And basically, after you do that, the luminosity, or the Eddington luminosity, is something like 3